1.3, complex numbers. These are all the objectives that we'll be going over today. And please mute your mic. And before we get into this, let's take a trip to, let's go to Egypt 4,000 years ago. You know what's interesting? Not that you asked or cared, but we are closer to Cleopatra, in terms of time, than Cleopatra was to the building of the Great Pyramids. I think that's pretty crazy. Like, the pyramids have been up that long. But anyways, let's take a trip to Egypt 4,000 years ago. All right, and we're going to count stones. And the way we count stones back then, we would say 1 stone, 2 stone, 3 stone, 4 stone, 5 stone, and so on and so forth. Right? And of course, you can just put something like this if you wanted to. But for the sake of this, we're going to use our Arabic numerals here. Okay, so instead of writing out tally marks, we're going to actually write numbers. Okay, so let's say that we have somebody. He broke his leg, and he's unable to carry big old stones for a little while, so he decided to just sit down and do some thinking. Okay, he don't have any PlayStations or anything, so he's gonna do some thinking, and he's gonna go, okay, so I got 3 stones. All right, if I take 3 stones and I add some number, okay, we're not gonna use X, we're just gonna use a question mark. I'm gonna add some number, and that gives me 30 stones. All right, and so he puts around a little bit and he figures out, okay, so I need 27 stones. Easy, okay? Now these numbers that I'm giving you, these are called natural numbers, okay? These are numbers that you see naturally. All right, you've heard integers, natural numbers, complex numbers, and real numbers. Did I say real? I don't know. All right, but these are natural numbers, numbers that you see naturally. You can see 3 stones, you can see 30 stones, you can see 27 stones. Okay. Well, now let's say that he's done with this thought process. So now he's going to go, okay, so I've got 30 stones. Okay, and I'm going to add what to my 30 stones to give me 3 stones. Okay, well, to us, since we've grown up in a very educated world, we can say, oh, that's negative 27. Okay, well, his buddies, after a long day of hauling rocks, they're like, you're out of your mind. What? This doesn't even make sense. Plus negative 27? That doesn't make sense. And his buddy's like, show me where negative 27 is located. Okay, and then our budding mathematician's like, well, I can't, right? So I can't show you where negative 27 stones are. However, it does exist mathematically, right? Okay, so the whole point of this is we're talking about complex numbers here. Right, now we might not be able to see complex numbers. They are unfortunately attached to the misnomer of imaginary numbers. Okay, and the thing is, they're not imaginary. They are indeed complex. They're very complex. Please mute your mic. They are indeed complex numbers. They're very complex, but they're not necessarily imaginary. Okay, they do exist. They do solve algebraic equations similar to negative 27. Please mute your mic. Similar to negative 27 being. One second. Joseph, please mute your mic. Anyways, where was I at? Oh yeah. So complex numbers, they're complex, they are imaginary, all that good stuff. But again, they're not imaginary. They're actually used to solve algebraic equations, similar to how negative 27 solves this algebraic equation. So let's move on. So this reads, it is easy to verify that x is equal to negative 1 in the solution to the equation x plus 1 is equal to 0. Okay, now consider the equation x squared plus 1 is equal to 0. So let's consider this. x squared plus 1 is equal to 0. All right, so x equals -1 is the solution to this equation. To check, we're going to substitute x equals -1 into the equation, and we see that it is indeed a true statement. I'm sorry, it is indeed not a true statement. So the fact the equation x squared plus 1 has no real solutions because any real number squared added to 1 is greater than 0. So when we read and it says any real number, and real quick, when I took this course as an undergraduate, I wasn't going into mathematics as a discipline. I was going into psychology. Okay, so whenever my professor would be like real number, I'm like, it's a real G, right? Like that's the real number. But they are categorized accordingly, and you'll see them in your review sections. But real numbers basically encompass every single possible number you can think of, right? So, for instance, and let's go ahead and do this. Actually, let's move this up. We'll discuss real numbers. All right, so we're going to start with the natural numbers. Okay, they're denoted by a funny looking N like this. The natural numbers, as we said on the previous page, are 1, 2, 3, and then all the way to positive infinity. Okay, and then next up we're going to have our integers. Our integers are basically all the natural numbers, but also the negative of the natural numbers. And I should put negative infinity down here. Negative infinity. Okay. And then from there we would have our, we'll say our rational numbers. Let's see. No, that's not even that. Our rational numbers, I believe it's a Q. Okay, and our rational numbers are all the numbers that are fractions, right? So between the numbers 0 and 1, there's an infinite number of fractions, right? There's 1/2, there's 1/3, there's 1/4, and then we go on to infinity, right? 1 over some number close to infinity. So that would be our rational number. So I'll just type this in as or I'll say all fractions. And then we get to the big boy, the real numbers. Okay, so the fractions, all fractions, makes sense because we're talking about numbers that exist as fractions. Well, real numbers can be numbers that don't exist as fractions, right? Like 0. I'm just gonna make something up. 1, 3, 4, 8, 9, 6, 4, 4. Right? I'm just gonna venture and to say that this does not make a fraction. Okay, so real numbers are every single number that you can possibly think of. So for instance, again, the number between 1/2 and 1/3, there's an infinite amount of numbers between those two numbers in the real number line. And lastly, what we're going to be talking about today would be the complex numbers. And the complex numbers are basically all the rational numbers, all the numbers that ever existed, I'm sorry, all the real numbers that ever existed, plus some I. So anyways, I kind of went off track a little bit there, but I think today's a pretty short lecture, so it's not a big deal. But so to recall what I was trying to get at, when we talk about real numbers, this is what we mean. And I just wanted to go over that because, again, when I was a college algebra student, when I heard real number, I'm like, all right, that's cool. They exist, right? That's awesome. But it's basically any number. Whew, okay, so if you're still with me, good job. Anyways, the fact that the equation x squared plus 1 has no real solution, again, right here, no real number, because any real number squared added to 1 is greater than 0. Does this equation have a solution? If so, what is the solution? Okay, so we can't actually solve it unless we know the imaginary unit, how to solve imaginary unit, right? And of course we have that definition. The imaginary unit I is defined by I is equal to the square root of -1, or equivalently I squared is equal to -1. And of course, let's zoom in on this. If we have I is equal to the square root of -1, and if we squared both sides, we do indeed get I squared is equal to -1. So that's why we write or equivalently. So this is, again, something that you've seen before, imaginary numbers, but we are going to go over it today. Okay. So something that we have seen before, and normally I would probably write this out, and let's just go ahead and do the whole thing. Normally I would probably write this out, but since I spent so long talking about real numbers, we'll just look at this. Turn your attention up here. We've seen this before. Okay, so let's start from I. We know that I is equal to the square root of -1, or equivalently, I is equal to I, right? All right, so if I is equal to I, and one moment, for some reason my zoom went down. There we go. All right, so I is equal to some I, obviously. Well, I squared, we saw on the previous page, is equal to -1. Okay, well now what about I cubed? Okay, well I cubed can be written as I squared times I, right? And we said that I squared is -1, and we said that I is just I, right? So we would have -1 times I, so we'd have a negative I. Well, what about I to the fourth? Well, I to the fourth is the same thing as saying I squared times I squared, which is the same thing as saying -1 times -1, which is 1. And then, of course, you've seen this before. You know where this is going. I to the fifth is the same thing as saying I to the fourth times I, which is the same thing as saying 1 times I, which is I. And, of course, we see that we repeat the pattern. I, -1, I, 1. Okay? So the whole point of this is that I to the fourth is equal to 1. So what we're going to do here, and we'll start with A first. We'll ask ourselves, okay, so how do I write I to the 43rd as I to the fourth raised to some power? Okay, so I to the fourth. All right, so whenever I try to write tiny here, it doesn't really work. I to the fourth times what looks like 10, right? And then times I cubed. Okay, well, we know that I to the fourth, excuse me, I to the fourth was what, 1, right? Because I to the fourth is 1, 1 raised to any power is 1, so this just becomes 1. And what is I to the third? When we look up here, we said I to the third is simply -I, so it's 1 times a -I, put that in parentheses, and therefore my solution is -I. Okay, well now let's for instance, let's not look at this in terms of, like this now, okay? Because many of you are going to be equipped with a calculator, and some problems are, I won't say enormous, but I mean, many of you could probably do this in your head, but for the sake of this exercise, let's do this B I to the, and let's do, yeah, we'll do 100, and then we're gonna make another one up, okay? I to the 100, okay? So what I'm gonna do here is I'm gonna put this in my calculator, okay? So whenever you put something in your calculator and you divide by 4, okay, so let's see here. Recall, and let's just use a number like 20. Let's put this in white. If we did 20 divided by 4, well, that's just 5, right? And let's try to fix that just a little bit. Give me some room here. Okay, that is 5. And then if you do recall doing something like this in 3rd grade or something, you'd say remainder 0. Okay, so let's do 21 divided by 4. Well, we'd say that's 5 remainder 1. And let's do 22. 5 remainder 2. 23. That's probably too close, isn't it? 23 is 5 remainder 3. And then 24 we know is it goes nice and smooth in there. It goes into it 6 times. Okay, so the whole point of this, if I were to put this in my calculator, if something is a remainder of 0, okay, that means we're going into it 4 times. So what I would do is I would say that it's equal to 1. Okay, so for instance, if I were to do 100 divided by 4, I would get 25 remainder. There's no decimal point there, is there? I would just get a solid 25, so that would tell me that 4 goes into it. So the answer here would be 1. Okay, and if I were to get a remainder of 1, remainder of 1. All right, well, if I put that in my calculator, that is, it would have a 0.25, correct? So let's say, for instance, I do I raised to the 101 power. Well, that would be, it would go into it, 25 times with a remainder of 1, but if I, put it in my calculator, it would be 25.25. Well, that 0.25 would correspond with that remainder of 1, and the remainder of 1 would tell me that it's just simply I. Okay, and then, again, if you do, let's do 102. 102 divided by, let's go ahead and write it out, actually. If we did I raised to the 102 power, not like that, 102 power. Well, if I put that in my calculator, I would get, something, it's 25, but something 0.5. Well, 0.5, right, is just, 2 left over, right? If something's getting divided by 2, there's a remainder of 2, so we would say it's negative 1. Hopefully I didn't confuse you too much. With that, let's go ahead and do C. And, oh, it's a 21. So let's erase that yellow down here, because we're going to need some room. So C, I to the negative 21. So in your review sections, you recall that anything raised to a negative power would just be 1 over that exponent, and that would get rid of your negative exponent, right? Well, I to the negative 21 power, and luckily we did it up here, right? Purely on accident, actually. 21 divided by 4, we said we 5 with the remainder of 1, right? Well, that remainder of 1 would correspond to this, which would just be I. So this is the same thing as just simply saying 1 over I. And complex numbers, here we have our rigorous definition here of a complex number. So we talked about imaginary numbers. Right, imaginary numbers go hand in hand with complex numbers because complex numbers are written in the form of that imaginary number. So this reads, now that we have defined the imaginary unit, it's time to introduce a new type of number known as the complex number. The definition, a complex number is a number that can be written in the form a plus bi, where a and b are real numbers. We often use the variable z to denote a complex number. All right, so what this is saying is instead of saying, 3 plus, and there's nothing wrong with saying 3 plus 4i, right? But if I were to say 3 plus 4i is a complex number, well, I can just simply denote that as z. So if I said z plus z, that would be the same thing as saying 3 plus 4i plus 3 plus 4i. Okay, so all it's saying is we typically use a z to denote a complex number. All right, and this goes on to read that a is called the real part. So the real part being, just simply this number, right? A is called the real part, and B is called the imaginary part. And B right here would be the imaginary part. And it goes on to kind of give the exact same thing that I did there. Okay, so this is where it gets a little tricky, but it's not too tricky. The number 5 is also a complex number because 5 can be written as 5 plus 0i. Therefore, Therefore, every real number is also a complex number. And this kind of goes back to, and I'm not going to get too much into it, but we talked about these sets, they get larger and larger as we go. Oh, that's actually pretty nice. They're actually larger and larger as we go. So, so basically we have the natural number. For if we go up into the integers contain all the natural numbers. If we go up, the rational numbers contain all the integers. And we go up there, the real numbers contain all the rational numbers, and then we go up, the complex numbers contains everything. Okay. So that's all that's saying. Therefore, any real number is also a complex number, again, because it could be written in the form 5 plus 0i. So I'm 33 years old, I think. Forget. You just kind of lose track as you get older, right? I'm 33 years old, but if my name was Sheldon Cooper, I would say I'm 33 plus 0 years old. I do not like that show, though, so let it be known. All right. adding, and this is actually, no, we'll do it. What time is it? Yeah, we'll do it. So whenever you add or subtract complex numbers, it's about as easy as you would expect, right? The adding and subtracting complex numbers, you can just kind of think of I as a variable. Obviously, it's not, but you just think about it that way. So we'll rewrite this without my parentheses. So 7 minus 5i, and then if it's an addition sign, it's not, it's just like saying multiplying through here by positive 1, right? So it becomes minus 2, and then plus I. And then what we'll do is we will combine our our real parts, and we'll combine our imaginary parts. So we've got the 7, and we've got this, but it's positive 7 and a minus 2, so that turns into a 5. And let's do yeah, we'll do that. No, I'm sorry. I'm just thinking aloud. So we'll do 7 and a minus 2. So we'll have a 5. And then a minus 5i and a plus 1 gives me a minus 4i. And that's A. B, 7 minus 5i. And again, same rules applies that you are familiar with. We have the negative in front of the parentheses, so we're going to distribute a negative 1 there, right? So it's going to be a minus 1 times a minus 2, or negative 2, so we get a plus 2, and then a minus I. So this becomes, we combine the 7 and the 2, we get a 9, negative 5 and a negative I, gets us a negative 6i. And that's it. We're done. Interestingly, I actually also go over complex numbers, imaginary numbers in my pre-calculus course. I went over it yesterday, and you can also find that video on YouTube. It's the latest video. Okay, now multiplying. Multiplying is where it gets a little tricky. Not much, as long as you memorize one thing. We'll probably put everything over here. Okay, so when multiplying two complex numbers, treat the problem as if the multiplication of two binomials. Just remember, and this is where we will highlight. Was that the highlighter? Just remember that I squared is equal to negative 1. Okay, so let's do this. We're going to multiply, and we'll go ahead and write this out so I can show the foiling process. Okay, so the foiling process, if you recall, is first. Foil stands for first, outer, inner, last. Okay, now it's really just the distributive property, but it's unique to two binomials. So we FOIL through, the first and then the two outers. So let's go ahead and do that real quick. Put this in green. So we got 28. Then we've got plus 20i. And then we're going to do the inners and then the two last ones. So we've got a minus 21i and then a minus 15i squared. Okay. All right, and then we'll proceed to solve. So we're going to combine like terms. We're going to have a 28, and then looks like we're going to have a minus I, and then we're going to have a minus 15, and it's a minus 15i squared. But again, what I highlighted up here, recall that I squared is equal to negative 1, so we're going to replace the I squared with a negative 1, like so, and then we can, we know it turns to a positive 15, right? So this is equal to 43 minus I, because negative 15 times a negative 1 is a positive 15, and then I just combine like terms, right? So I said it's not, I mean multiplication is a little harder than addition anyways, right? So, but it's just a little difference. Just recall that I squared is equal to negative 1, and you have the multiplication down. Well, what about, division. We now define the complex conjugate. So recall that a conjugate is basically anything in the form, A plus bi, well, let's just do a plus b. We're just talking about conjugate. Okay, a plus b. All right, well, the complex the conjugate would just basically be the sign is different. That's it. All right, and so the complex conjugate follows the same rules as a conjugate, except it involves complex numbers. And then we see the definition here. The complex conjugate of a complex number, z, as we mentioned before, plus a is equal to a plus bi, is denoted as z bar. There's a bar over to z. I don't know if you can see it or not, but if the complex number is denoted with z, its complex conjugate is denoted by z bar. All right, or you can say a plus bi, put the bar over that. Excuse me, which is simply a minus bi. And for example, the complex conjugate of this, z is equal to negative 2 minus 7i, would simply be negative 2 plus 7i. Okay, so we see the complex conjugate. All that changes is that middle sign. And why is this important? Let's find out. All right, it's interesting. This theorem here is actually not in my pre-calculus text. And so I had to come up with that. I had to show it by myself yesterday. Page. And I just went ahead and skipped the whole thing because this is just simply foiling, and I'm not going to do that again. So this is reading, multiply the complex number z is equal to negative 2 minus 7i by its complex number. The z bar is equal to negative 2 plus 7i. Okay, we just do z times z bar, and of course it's just the two binomials and their conjugates. Negative 2 minus 7i, negative 2 plus 7i. They're just complex conjugates. You foil through all that good stuff. You combine like terms. Obviously, since they're conjugates, the middle terms cancel out, similar to how they would cancel out in difference of squares. And you end up with simply a 53 as an answer. Okay. And then what we read down here, notice in example 5 that the product of z is equal to negative 2 minus 7i and its complex conjugate is a real number, the real number being 53. In fact, every complex number, when multiplied by its complex conjugate, will yield a real number. The following theorem is worth remembering. This is definitely worth remembering, 100% worth remembering. It reads, the product of a complex number and its conjugate is the real number a squared plus b squared. So let's go back and actually look at that. Okay. So we have the complex number, negative 2 minus 7i, and we'll just go ahead and denote that as z. And then we had the complex conjugate as negative 2 plus 7i. What this theorem is stating, and it will save you a lot of time, what this theorem is stating is that if you multiply them together, it's just a squared plus b squared. So really, all we have to do is hone in right here. That's all we got to do. Just hone in on one of these two. Not a big deal. Doesn't matter which one. But we'll just look at this one. Okay. Well, we're gonna look at the value of a. If it's in the form a, and bi. Well, 2 squared is 4. And negative 2 squared is 4, right? Negative 7 squared is 49. And that's equal to 53, which is right there. Okay, so this theorem is 100% worth memorizing. It's not, I don't think it's monumentally hard, but at the same time, if you just want to fill things out, take your sweet and precious time, that's fine. But in the real world, speed is good, right? You want to impress your employers, so think quickly. Okay, and I think actually that's the last example, isn't it? No, it's not. Okay. Oh, we can actually go to 8. Okay, so example 6. Okay, this reads, the goal when dividing two complex numbers is to eliminate the imaginary part from the denominator and express the quotient in the standard form a plus bi. We can do this by multiplying the numerator and the denominator by the complex conjugate of the denominator. Okay, so similar to how we would rationalize denominators, rationalizing denominators basically is we got rid of the radical in the denominator. Okay, and you might be thinking, well, you know, what's so wrong with saying, you know, 3 over the square root of, you know, 3? What's so wrong with that? Well, I mean, on paper, it's not such a big deal, but whenever you get into computation, especially hand computation, it just becomes significantly easier to get rid of a radical in the denominator. Putting in the numerator, just fine. It's totally fine. But like, you know, trying to get a common denominator and stuff like that of a square root of -3, it's kind of tough. All right, and the same thing kind of revolves around having a complex number in the denominator. So what we're going to do to get rid of the complex number in the denominator is we're just going to simply multiply by the complex conjugate. Okay. So real quick, again, I'm 33 years old. Okay, if I multiplied my age by 5 plus 2i divided by 5 plus 2i, that, I mean, it's a stupid way, but that's another way to write 33, isn't it? Because what is 5 plus 2i over 5 plus 2i? Well, that's just 1. That's 33 times 1, and I'm still 33 years old, right? I'm not changing my age at all. All I'm doing is just, you know, making it a lot more complex to say, right? And that's kind of what we're doing here, right? We're going to be multiplying this by 1. Okay, we're going to multiply it by 1, but it's going to be a prescribed one. It's going to be a fancy one, okay? So what we're going to do is we're going to multiply it by 5 plus 2i over 5 plus 2i. Okay, and then we proceed. And honestly, let's go and do the denominator first, right? From the excuse me, from the previous theorem, we know that it's 5 squared plus 2 squared. Okay, so 5 squared is 25, 2 squared is 29. So I'm just going to go ahead and write that as 29. That's easy, isn't it? All right. The numerator, not so much. We're going to have to actually FOIL and all that good stuff. So let's do that. Okay, so 1 times 5 is 5. 1 times a 2i is 2i plus 2i. Negative 3i times 5 is a minus 15i. And a negative 3 times a positive 2i is a negative 6i squared. And we'll do that. Okay, so let's combine like terms. And let's actually put it down here. Okay, so we're going to have, let's change colors. Now let's take it. So we're going to have the 5, you know, that's going to stay, okay? We have the 2i and the negative 15i, so we're going to have a minus 13i, and then a minus 6i squared. So we know that the negative, or the I squared is a negative 1, right? So it's basically saying negative 6 times a negative 1, which is going to be a positive 6. Plus 6. Okay, well then we can combine these like terms, right? So I'm going to go ahead and add the 5 and the 6, so that's going to be 11. And then all over 29. And you would think, well, we're done. And, you know, we are mostly done, okay? This is saying write the quotient in the form a plus bi. And many of you are going to do this on your homework. You're going to put this down and you'll be done, and you're going to get it wrong. But luckily you have 3 chances, and hopefully it'll hit you. Oh, Professor Brown said we got to put it in form a plus bi. Okay, well, how do I write this in the form of a plus bi? Well, it doesn't take much from here, right? We have a common denominator of 29. We're just basically going to do the reverse of what we have been taught to do when we have a common denominator. So instead of combining the denominators, we're going to split it up. So it's just going to be 11 over 29 minus 13 over 29i. And that's it. All right, so in section 1.4, we solve equations that often lead to solutions with negative number inside of a radical. I don't remember, we're in 1.3, aren't we? Well, thanks for telling us what we're going to do soon. Therefore, it is important to learn how to simplify a radical that contains a negative radicand. Okay, radicand is the number inside. We simplify such radicals using the following property. Remember that negative 1, the square root of negative 1 is equal to I. So here's the property, super duper easy. If m is a positive real number, then the square root of negative m is equal to this, we can split it up into the square root of negative 1 times the square root of m, and since we know the square root of negative 1 is I, we can just write it as I on the square root of m. Okay, and here is a thing that we might, I'm pretty sure we'll address this later, but for the sake of this, I'm going to address it now. Square root of negative 2 times the square root of negative 3. Okay, in your review sections, you might have had a problem that looks something like this. Okay, and of course we're taught, well, we can just combine that to be the square root of 6. Okay, so if we had the square root of negative 2 and square root of negative 3, well, that's just the same thing as saying, you know, the square root of negative 2 times negative 3, which is the same thing as saying the square root of 6. Okay, but that's wrong. The reason why, and this is where, you know, people will be like, you know, math doesn't make sense. Well, you know, truth is, math is the most logical discipline that there possibly ever could be, right? A book written 3,000 years ago is just as right today as it was 3,000 years ago in mathematics. And the reason why it's consistent is because whenever you looked at the definition to perform this, multiplying radicals, the whole premise of this was that these numbers must be positive. Okay, well, in this case, they are not positive. Maybe in this case, they are not positive. So that rule that we saw in the review section of multiplying like radicals cannot be used. So we must use another property, and this would be multiplying radicals with a negative radicand. So that's just a quick little soapbox moment. Okay, I guess the undos have a limit. All right, so example 7, simplify the square root of negative 108. And the first thing I'm going to do, you know, I'm just going to write I on the square root of 108. Okay, excuse me. And of course, to get there, it would be to just go ahead and, you know, if you wanted to, do negative square root of negative 1 times the square root of 108. And then, of course, the square root of negative 1 is I, and then we have times 1 square root of 108. Okay, which is exactly what I have down here. Right, but again, I skip the white part, and I'm just going to pull an I out. That's it. All right, and then when I pull the I out, I now have the square root of, or I on the square root of 108, and then we'd have to simplify this radical, and that would be 36 times 3. And we know the square root of 36 is 6, so we would say 6i on the square root of 3. Okay, that's just simplifying the radical. There's a bunch of problems. Okay, and I'm pretty sure, like, I think this was the last example. All right, so we've got the A. We'll do A. 1, 2, 3, 4. Okay, we can do them all in different colors. So we can rewrite. We'll just go ahead and rewrite this, right? Like, I'm just going to go ahead and do I on the square root of 8 plus I on the square root of 18, and then proceed from there. Well, I know this can turn into 8. It has a perfect square of 4 times 2, and the square root of 4 is 2, so that's a 2 on the square root of 2. Similarly, 18 is comprised of 9 times 2, 9 being a perfect square. So I would say, this is actually good. This is okay. Let's actually zoom in on this real fast. So I pulled the I out. Okay, that's what I did here. I pulled the I's out, and then, you know, I know that 8 is 4 times 2, and I could take the square root of 4 out, and that's where this 2 came from. Okay, and likewise, the 3 that I'm going to be pulling out would be the square root of 9, because 18 is comprised of 9 times 2, right? So it would be this on the square root of 2. But I can rewrite this, okay? I2 on the square root of 2, that just looks kind of silly, doesn't it? Right? So I could rewrite this as 2i and 3i. Okay. And then we combine them, so we've got 5i on the square root of 2. B. That we are multiplying now, okay? So again, do not do this. Do not combine them under a radical, because I mean a negative times negative is always going to be a positive, right? So we're going to have to do the rule that we saw on the previous page, and we're going to have to go I on the square root of positive 8 times I on the square root of 18. Okay, well, 180, 36. So it's going to be equal to I squared on the square root of 144, I squared. Okay, we know I squared is a negative 1. We know the square root of 144 is 12, so it's going to be a negative 12. Oh man, C, I'm not really in a hurry to do C, but we'll do it. C, we've got a negative 6. And I'm just going to go ahead and do the arithmetic involved here, right? So like I'm just going to write 36 and then what, 40, right? So I'm going to go ahead and go about doing that. So we've got negative 6 plus the square root of, I said 36 and 40, so 36 minus 40 is a negative 4. And all of that is over positive 2. And then I can write this as negative 6. And then I'm going to go ahead and pull an I out, right? So I'm pull an I out, and it's the square root of 4, right? Well, we know what the square root of 4 is, right? We know it's 2. So we can just rewrite this as 2i over 2. And then I said before that we can, we rewrite this in the form of a plus bi. So this would be a negative 6 over 2 plus 2 over 2i, or in other words, negative 3 plus I. That's C. And D, I wonder what we got to sort for D. That would be 4. It's in the numerator. Make it a little bit smaller. 4 plus or minus the square root of 12, square root of negative 12. So I'm going to go ahead and take the I out there. 12 over 4. Okay. Well, the square root of 12 we know can be rewritten as what, 4 times 3, and 4 is a perfect square, so we can pull that 4 out. So this would be 2 on the square root of 3. 2i on the square root of 3. Okay. And from here, we know that we can rewrite this as 4. We can actually take a 2 out. We're not going to do that. It would be 4 over 4 plus or minus 2i on the square root of 3. And let's just do this. So let's remain consistent. And we'll put 2 on the square root of 3 over 4i. Okay. And then from there, we will have 1 plus or minus the square root of 3 over 2i. All right, and that's it. I'm pretty sure that concludes the lecture. Yeah, we're on the exercises, so that concludes the lecture. I'm going to stop the recording.